First of all, I would like to thank organizers for invitation, for running this very nice conference. This is third time when I am at Malta. Each time I enjoy being here, at least two different dimensions. Very good friends in mathematics. It's a pleasure to communicate with them professionally, and very surprising hospitality of people at Malta. So difficult to say that what is more attractive. I think both issues are very attractive. Before I will start, I would like to start from apologies. This is a joint presentation with Leif Jonsson, who is here, and with my former PhD student Matan Zivav from Beersheba. It was expected that Matan will be responsible for help with preparation of slides. Unfortunately, he has some chronic disease, and he has now splash of this disease. And by this reason, he was not able to finish slides. So at some moment, slides will be really horrible. So I'm very sorry about this, but I didn't have escape. Or I will cancel my talk, or I will continue with these horrible slides. So you will see when they will come horrible. But at the beginning, things will be reasonably good. Roughly speaking, I can divide my lecture into three parts. First part will be a kind of educational kindergarten introduction to the area of association schemes and coherent configurations. This is traditional part of what is called algebraic graph theory, but I believe that most part of people here are doing what we call traditional graph theory, and probably they are not aware with our concepts. So I think it's a good idea to help them to better feel these starting concepts. After that, I will talk about more special things. This is total graph coherent configuration. And finally, at the very end of the lecture, I will talk a little bit about our new results. And as was said by Joseph, that those who are interested to listen more can go to a lecture by Leif, and he will talk about more striking and more deep recent results. Okay. So let's start from topic algebraic graph theory. Two names are attributed to this area. One name is algebraic graph theory, and another name is algebraic combinatorics. And in algebraic graph theory, we would like to find some nice structures. Nice means highly symmetric structures. And what does mean high symmetry can be described in different terms. Ideal situation will be that high symmetry means that we have very rich automorphism group. I will not explain what does mean rich. There are a lot of possibilities to speak about transitivity of action of automorphism group on one or other kind of substructures of graph. Another way is to require spectral properties of graph. For example, one of the requirements is to talk about graphs with 3 eigenvalues. And the final requirement is to speak about some nice parameters of graphs. So this is what is going on in algebraic graph theory. The name was coined by Norman Biggs, and it was coined in his seminal book by 1974. There is second edition. And now paradoxical things are coming. I am afraid it's difficult for me to use microphone. Probably I will give up with microphone. And I think that my voice is reasonably good. And I think that everybody will be able to listen to me. And it's much more easier for me to talk to them.
They won't get it on the video.
I'm sorry. Sorry. So, Biggs, in his seminal book, coined name algebraic graph theory. For a while, this name was very popular. After that, Barney and Ita created another name, algebraic combinatorics. But after that, this name was occupied by people from very respected area, people around, I would say, Robert Stanley, Giancarlo Rota, and then it was very difficult for us to compete with people from this area, and it was not some commitment, it was more or less done occasionally, but most part of people decided to call this area algebraic theory, and there are a few very nice books in this area. Last book is by Chris Gottsuk, who is here at the Royal, and there is a book which we call Bible. Bible is borrowing Cohen Neymar. This is distance regular graphs, and still people who are working in this area, if they discover something nice and beautiful, first of all they have to go to Bible and to be sure that this was not known to people in Bible. Only after that they have chances to think that something new really was not there. Now we will start from the concept of centralizer algebra of a permutation group. So I will talk on very naive level. So what is permutation group? We have a symmetric group of degree n, which is acting on n points. A typical way for computer to define permutation group is to give a set of generators. Sometimes people are struggling for compact set of generators. But for us, especially in this lecture, permutation group will appear as a group of symmetries of something. This means we have some nice structure, and we would like to consider our permutation group as automorphism group of this nice structure. So let's start, as I said at the beginning, I intentionally work with what I call kindergarten example, and by this reason I really will work with very simple examples. So we have alternating group A4 of degree 4 of order 12. I believe everybody in this audience will agree if I will say that the easiest way to explain what does mean this group, this is group of rotations of the tetrahedron. But here appears some difficulty. When I'm saying a rotation of the tetrahedron, this means that I have some physical body, and I'm thinking in terms of geometrical transformations, and I would like to consider this on the level of relations, because everything in graph theory and in its generalization is related to relations. So I will start from explanation what does mean alternating group of degree 4 from use of relations. So we say that we have first of all list of permutation, it is given here. We can introduce A4 with two cycles of length 3. It is two transitive. This means that it's acting transitively on ordered pairs of points. And if I would like to introduce this group as an automorphism group of some relation, then this relation can be very easily described. I will give four-oriented triangle F1, F2, F3, F4. The idea, if one will think about orientation of tetrahedron simultaneously, right or left, here I was talking about right orientation, but I consider this as a relation of arity3. And then, in my eyes, A4 is automorphism group, which permutation group, which preserves this relation. And in our language, this means that A4 has arity3. And arity of permutation group is a number in interval from 1 to n minus 1. And for example, permutation groups which have arity 1, these are very simple groups, for example, some direct product of symmetric groups, because here we have some partition. And in graph theory, we are interested in permutation group of arity 2, because graph is nothing else but binary relations. But in this area, we are working with, first of all, with directed graph. I will recall what that means graph. The directed graph consists of vertices and directed arcs. And we are working with color graph. Here, there is place for misunderstanding. When we speak about color graph, we mean the following. We mean that we have a full directed graph, and we attribute colors to some arcs of full graph. And each arc of full directed graph is getting some color. This is our concept of color graph. So a little bit different from what people are using in traditional graph. And automorphism group of color graph preserves each color separate. In principle, we can consider a larger group when colors is allowed to permute and something else, but mainly in this lecture we will consider automorphism group of color graph, which is in this traditional. Now, next very significant concept is a centralizer algebra of a permutation group. So we start from permutation group G omega of degree n. We consider each permutation as group of permutational matrices. It's easy if we have permutation which is acting on the set of cardinality n. We can consider matrix of order n by n, and if in each row and in each column there is exactly one unit and all other units are zero, this is what is called permutational matrix. So we represent our permutation group as group of permutational matrices. Now we consider algebra of all square matrices of order n. And in this algebra, we consider centralizer of our permutation group. And the centralizer is a subalgebra of this algebra. And this is called centralizer algebra of a permutation. This concept goes back to Schiller, a very famous mathematician. He mainly was working in Germany, but he finally was forced to emigrate to Israel, and he died in Israel, I believe, and his birthday was 66 years of his life. He was very confused. Now, when we are working with centralizer algebra of permutation group, it has a very special standard basis. This standard basis consists of 0, 1 matrices, and we can interpret these 0, 1 matrices as adjacency matrices of directed graphs. And this allows us to switch simultaneously from one language to another language, and vice versa. We can start to talk about matrices. We can, after that, go to relations, and after that, we can return to matrices. I will give later an example that you will be able to observe how such switching is doing. Okay, now I consider a little bit more sophisticated example, so-called induced action of group A4 on 6 points. So now my alternating group A4 acts on the set of 4 elements, which are denoted A, B, C, D, and I consider as omega set of all 2 element subsets of this set. Clearly, we have 6 such subsets, and I consider induced section of this induced section of alternating group. And it turns out that our centralizer algebra has rank 4. To understand why rank 4, you can very easily look at the picture. We have directed graphs, which is denoted by R1. We have a graph R2. R2 will mean that we switch direction of all arcs to opposite one. We have R3. R3 are non-diagonals of this diagram, and R4 is groups. So in our relational language, we have very clear description of basic groups. But we can simultaneously describe this in metric language. And in metric language, we are doing the following trick. we simultaneously consider adjacency matrix of 4 previous graphs. And we denote them by A1, A2, A3, A4. And after that, on position of each matrix, we are writing O1, O2, O3, O4. So we have such full matrix of size 6 by 6. And if we read this matrix, we can see in matrix language, and if you would like to translate language of graphs, our code. And here, clearly, rank is equal to 4 because we have just 4 different elements which appear in our full matrix. Very significant is that our permutation group is not too close. What does mean too close? Too close means that it is not automorphism group of some color graph. In fact, it is semi-close. We can again consider some set of triangles. I will not tell you about these details. I just would like to make reference why this permutation group is not too close. This is very relevant to very famous Whitney-Young theorem in graph theory. The trouble is that if we will consider the permutation tau, which is interchanging complementary two-element subsets, for example, AB and CD, AC and AD, and so on, then it is very easy to check that this extra permutation, which definitely does not belong to our induced group, preserves our graph. So this is example of situation when we have permutation group, which is not two groups, but it is 3 groups. Now we go back to the concept of coherent algebras. So, first of all, I will explain what is going on some philosophical level. So, I introduce more or less rigorously what this means centralizer algebra of a permutation. Now we would like to make a generalization of this concept on purely combinatorial level. In a sense, we would like to imitate some significant properties of this centralizer algebra. It turns out that this was done by 2 independent group of researchers, Boris Westphaler and Andrei Lehmann in Moscow, both my friends, and Donald Hickman in United States. At the beginning, these two approaches were developing independently. Only after probably 5-6 years, most artists became acquainted about achievements of each one. So, coherent configuration of coherent algebras, again, if we are using a language of matrices, then we speak about coherent algebras. If we speak about relations, then we speak about coherent configuration. As I said, they appear as a combinatorial imitation of permutation groups. And if you speak about algebra, in algebra there are definitely structure constants, because if we have standard bases and we multiply 2 elements of bases, then product of 2 elements of bases is linear combination of elements of bases, and then we are very naturally reaching structure constants. But these structure constants sometimes are called intersection numbers, and they are nothing else but as number of special blocks in color graph. So roughly speaking, we fix some arc from one point A to point B, and we count how many different ways of length 2 can be done with some prescribed properties, and these are our favorite structure constants. So here, as soon as we are giving this generalization, note that I intentionally are not giving precise formulation of axioms. This can be done, but my experience shows that it is not helpful, because if people are familiar with these axiomatics, they remember it by heart. If they are not familiar, if I will spend a couple of minutes and will write this axiom on blackboard, it will not be too helpful. So, instead of discussion of axiomatics, I prefer to discuss if this axiomatics is more general in comparison with the concept of centralizer algebra of permutation group. The immediate answer, yes, it is more general. And the question about equality of such axiomatization goes back exactly to such thing. When he introduced this concept in very concrete case of so-called group rings, they nowadays are called, due to Helmut Wheeler's, sure rings. And he didn't know if there exists example of what is now called sure rings, which are not coming from a suitable permutation. Only later on such examples were discovered. A lot of such examples are now known, and we'll in a minute talk about such examples. So, first of all, terminology. If object is coming from a suitable permutation group, we call it Shurian. If it is not coming from permutation group, this means that it is purely combinatorial, then we call this object not Shurian. It turns out that the smallest non-Shurian objects for a long while were existing on 15, 16, and 18 vertices. And I will show you first guide. This is for a long while the smallest non-Shurian object on 15 points. This is so-called doubly regular group. You are working in graph theory, you know that there is some tradition to give such nice picture, it looks very nice, but when we look at this picture, we typically cannot find something from it. So this is a kind of aesthetics, but nothing else. So let's look at this picture as a description of something in algebra. So this is so-called doubly regular tournament, and it is doubly regular tournament. We have tournament gamma, we have opposite graph, gamma transpose, we have loops. So this is coherent configuration of rank 3. Its parameters are 15, 7, 3, 4. And if you would like to understand very briefly what this means, this means that take adjacent symmetries of this directed graph, find its square, and square is a linear combination of two matrices A and A transpose with coefficients 4 and 6. And it turns out that exactly this example is not Shurian. The fact that it is not Shurian was proved by Nino Pasichin. And the proof, provided we are using computer, is very quick. With computer, we are finding that the automorphism group of this nice picture has order 21, and recall that we have 15 vertices, and this tournament has 105 arcs. So if this is Shurian, then by definition, automorphism group has to walk transitively on vertices and on arcs. But clearly 21 is not multiple of 15, 21 is not multiple of 105, so we are done. This object is not Shurian. But it turns out that it can be proved in purely combinatorial pyramids in the following manner. We just have to distinguish arcs. We can find combinatorial invariant some induced subgraphs with 5 vertices which are sitting on particular arc. And it turns out that with the aid of such invariants we can distinguish arcs, and to prove purely combinatorial, the object is not true. And there is very nice theorem, I believe due to Peter Rawlinson, that if we will work with 4 induced subgraphs of size 4, it will not work. So the smallest case when we can try to manage to distinguish is 5. Now coherent configurations permit 2 fibers. First of all, I will explain what is a fiber, because this concept was not appearing still. So first of all, association scheme is a particular class of coherent configuration where all groups form one basic graph. In general, this is not the case. In general, groups can be split into a few parts, and then each part is called fiber. And one can say that fiber is a combinatorial analog of orbit in permutation group theory. And fiber, and it was Hickman, Donald Hickman, who suggested to pay attention to coherent configuration with two fibers. His motivation was coming from so-called strongly regular designs. I will not give now accurate definition. Roughly speaking, this is a kind of combination of two concepts very popular in design theory and in graph theory. On one hand, we have strongly regular graph. On the other hand, we have a symmetric design. If some axioms are working together, then we are coming to strongly regular design. And recently, Matanzilov, who is author of this lecture, found a non-Shurian example of coherent configuration with two fibers on 14 points, and fibers have size 6 and 8. This was a real sensation. It was probably for good, since Ivan Pasechnik was in previous century, so probably for good 20-25 years, there was no progress with smaller objects, so it was very pleasant surprise. We now have very nice computer-free interpretation of this structure, but moreover, now there is full computer-aided enumeration. We know that all coherent configurations on up to 13 vertices are Shurian. On 14 vertices, there is just one example, non-Shurian, which was discovered by Matanzilov. On 15 vertices, there are just two objects, all object and one with extra points. But when we go ahead with 16 vertices, then there is a usual combinatorial exposure. There are dozens of such non-Shurian objects, and of course, if we increase the size of our object, then there is a situation that probably more non-Shurian objects in comparison with Shurians. In our lecture, more accurately we can say tandem of lectures, we pay special attention to so-called total graph of coherent configurations. And in a row of initial graph for total graph, we will consider a few concrete examples. But before we will go ahead, I would like to tell a little bit about used computer tools. So, first tool is COCO, coherent configuration. It was created long time ago by Igor Karajev and my assistants. And this is very simple package, which is working without any extra system like Magma or GEM. It has 6 main functions, which are described here. Probably the most surprising function is a program to calculate the automorphism group of a coherent configuration and its fusions. It depends on what is automorphism group. If automorphism group is imprimitive, then we have some difficulties. But my experience shows that if automorphism group is primitive, then we can work with graph which has a few thousands of vertices. We can find automorphism group of such graph in number comparable with fusions. Okay. Another tool is GEP. Everybody knows GEP. Very significant that GEP is used by us in conjunction with GRADE. And GRADE is packaged which was created by Leo Switcher, and by default it is used also now by Brandon with. And GEP we are using for a lot of different activities. Activities with groups, activities with graphs. I will not read the list of these activities. Again, my partner Matanzilov is very good in working with GEP. Typically, he is living on the south of Negev and quite rarely here in Beersheba. So typically, I sit down at the evening, we both are like birds over the phone, and I'm working with him for a couple of hours, put questions, what can be done in GEP. is pushing buttons, and in a couple of minutes we are getting all returns. So it's working surprisingly efficient. Okay, now I would like to give you a kind of example, which I call preliminary example. So we start from diagonal group D5 of order 10, which acts naturally on 5 vertices. This is nothing else but automorphism group of pentagon. But we are considering simultaneously 2 copies of pentagon. This means one copy has vertices from 1, 5, and one copy has vertices from 6 to 10. And we are describing 2 orbits of this intransitive action of our permutation group. Sometimes they are called orbitals. This is a subset of this. And we would like to look at the coherent algebra. And this is Coherent algebra. This is Centralizer algebra of our permutation group. And now, very significant picture. If you will understand what is going on in this picture, this means that I didn't do my job in vain. Something you will understand from this picture. So, what is going on with this lecture? Just a moment. Okay. So here we have first of all 2 copies of pentagon, external and internal. So, sorry. Okay, so these are loops which are on external. These are loops which are on internal. These are edges on external copy. These are edges on internal. This is complementary graph on external copy. Let me see where. Here. And this is complementary graph on internal. And besides this, we have 6 pairs of graphs such that we go from external to internal and vice versa in all possible ways. And easy count, it shows that the rank of such algebra is equal to 12. This is centralized algebra of permutation group, which has 2 fibers. Fibers have length 12. Now what we are doing with this object? We are using this object as a kindergarten constructor. And we would like to construct from it some nice graphs. And let's go ahead. We are asking Coco to construct so-called fusions. Fusions, this means all association schemes which appear in as some algebras of this coherent algebra. Here I am discussing 50 such fusions. And among them, there are 2 very nice fusions. These are 2 incarnations of Peterson graph. First Peterson graph is well known, everybody knows this copy. But there is another copy, I will say steal copy of Peterson graph, this one. And even in this small example, if we will take a person and will ask him which copies of Peterson graph can be constructed from this set of relations, it's not immediately evident. And advantage of Coco is that it is doing this in a few seconds, and we are getting a reply automatically. Okay. Now, again, I repeat that we'll later on, if there will be some time remaining, we'll make return to this example, at least on conceptual level, and I will explain you why this preliminary example is reasonably significant. Now, total graph coherent configuration, first exposed. So first of all, I have to explain you what does mean total graph. Formal definition is written here. But let's explain this in words. I believe it's much more easy. So we have the initial graph. Yes, we are working with simple graph. And the vertices of total graph are vertices and edges of initial graph. Now, what is adjacency? Adjacency means that 2 vertices of initial graph are adjacent. 2 edges are adjacent if they have common vertex. And also vertex and edge are adjacent if they are inside. So this is usual concept of a total graph. And in principle, it can happen that automorphism graph of initial graph delta is smaller, strictly smaller. It's always smaller or equal than automorphism group of total graph. And for example, trivial example, K2 tells us that total graph of K2 is K3, and by this reason, here we have non-equality of automorphism. There are some more or less trivial properties of total graph in comparison with initial graph. For example, if initial graph has a rare value of valency k, the total graph has valency ok. But very significant that if we work with strong irregular graph and it is not primitive, primitive means that strong irregular graph and its complement are connected graphs, then automorphism group of graph and automorphism group of total graph are equal. So this is what we are assuming included in our experiment. Now we consider coherent closure of the total graph. Concept of coherent closure was not considered by me. This is the smallest coherent configuration which is included our initial graph. Again, Mikhail created a polynomial time algorithm for the construction of coherent closure. This algorithm became very, very popular recently due to the results of Algebraic regarding graph automorphism group. He is using some standard and more clever version of Mikhail standardization. So I'm using this concept in this. Now, in principle, when we are working with total graph coherent configuration, we can talk about two kinds of corresponding coherent configuration, so-called Theory&Combinatorial coherent closure and Combinatorial coherent closure. Theory means that we consider Centralizer algebra of automorphism group, and Combinatorial closure means that we employ Mikhail stabilization. In principle, Mikhail stabilization can be slower than Theory closure. But in our cases, which we are discussing, they coincide. So this is very significant. We were considering two nice classes of graphs, classical strong irregular graphs in graph theory. These are triangular graphs and lattice square graphs, and we proved theoretically that both definition of total graph coherent configuration coincide with this. Now I would like to talk a little bit about triangular graphs. So, initial motivation of our interest was of very concrete nature. We were working with infinite class of strong irregular graph, classical graph. Triangular graph is nothing else but line graph of complete graph. It is classical strong irregular graph. We constructed for this triangular graph total graph, and we were willing to describe for them total graph configuration and to see if there appear some interest in subalgebra or in irrational language interest in mergers. And the answer, it was obtained a while ago by Malta, that usually there is no such mergers. But there are a few exceptions. N is equal 5 and N is equal 7. So this was briefly what we are doing. Here I am talking a little bit with more details. So triangular graph is line graph of complete graph. If somebody is thinking here parameters of this graph, well-known result, classical result, that this graph is defined by parameters uniquely. If n is not equal to 8, or n is equal to 8, there are some examples. Some people will call it Johnson graph with parameters j and n. Now, if we will construct the coherent configuration for, first of all, algebraic or Coherent coherent configuration, for n is at least 6, it has rank 26. And structure constants are polynomials of in n of degree at all 3. And this can be done unitarily But before we speak about structure constants, I would like a little bit to tell you description of basic relations. So, as I explained generally, rank is 25. So, there are two ranks of relations. There are relations within first fiber. There are relations between first and second fiber. There are relations on third fiber. And our total graph in this notation is obtained as union of 6 concrete relations. 6 is very significant. I will use this number a little bit later. And now we wanted to construct structure constants. And there are 2 ways to construct structure constants. Let's go ahead. I will go first way, honest way. Honest way means that we are working with some combinatorial interpretation of structure constants. We are making some manipulation, and we are getting value step by step of each structure constant. This is polynomial linear. This is polynomial of degree 3. And I constructed 2 occasions of structure constants. But we have a coherent configuration of rank 25. We need tensor of structure constants. And tensor of structure constants includes 25 in power 3 of numbers. And each number is polynomial of degree at most 3. So if we will honestly make such computation for each structure constant, it will be very, very annoying and very sophisticated way. Instead of this, we created a very nice trick. First of all, at the beginning, we were willing to use Grosvenor basis, but after that, we realized that nobody of us is really good expert in Grosvenor basis, so we gave up with the idea to use Grosvenor basis. Instead of this, we created the following trick. We know theoretically that our structure constants are polynomials of degree at most 3. Then we are working with Coco, and Coco returns us the structure constants for a few values of n. And after that, we are using a Lagrangian interpolation. And the Lagrangian interpolation is returning us all necessary polynomials. So this program was written by Mikhail, and he obtained what is necessary. After that, did all necessary proofs, was working with structure constants as polynomials, and then finally he found result, which I was mentioning, that there are a few trivial merges. I will not discuss them too much, and there are a couple non-trivial merges which appear for exceptional cases 5 and 7. Now I still believe that I have a little bit time. I would like to talk briefly about cases 5 and 7. In the case 5, we get a very interesting Schurian association scheme of order 40 and automorphism group of order 1920. We, long time ago, managed to find its computer-free characterization. I will not talk about this today. But there is another also very interesting Schurian association scheme on 40 points, which has larger group. And this object for a long while was a puzzle for us. And this object I will discuss later on for a couple of minutes. But before this, I would like to talk a little bit about case n is equal 7. In case n is equal 7, when we are using Coco, Coco returns us that we have a margin, and this margin is a huge rank 3 automorphism group of order which is written on the record. And it turns out that after some investigation, we realized that this corresponds to the classical Zara graph on 126 vertices. So I now would like to talk a little bit about this object. So now we are interrupted. So I have to increase my letters. Hopefully I will succeed. So you understand our teaching technology. It was expected that Matan will type this portion of material which I created for him, but due to his illness because of the food. Sorry. So, we started with Coherent. Our initial action was intransitive action of symmetric group of degree S7 on two orbits. One orbit has length 21, other orbit has length 105. And Coherent returns us, as I a few times told, some trivial mergings, which I don't want to discuss, but there was some non-trivial merging. And non-trivial merging is written here. This is strongly regular graph with valences 1, 45, and 80. And this strongly regular graph appears if we start from triangular graph, then set of vertices has 2 orbits, and as I mentioned, set of edges has 6 orbits. And we would like to play the following game simultaneously. To understand graph, this is one line of activity. To understand group, this is second line of activity. And to interpret our object in terms of small knowledge of group, because S7 in comparison with the entire group is a relatively small object. And motivation, I believe Leif Jonsson will speak about this much more accurately, more probably I will manage also to talk 1 minute about this. That it's very significant for us to be able to see object with high group grouping from relatively small sample. Okay, so our results were the following. First of all, we proved honestly, without use of computer, with our graph is strongly graph with these parameters. I will show you protocol of proof here. This is protocol why this graph is regular. You can see that in each row, sum of elements, which is in a row, is exactly 45, and this is giving us proof that our graph is regular of length 45. If we will be more accurate and we will create 2 special tables, then we will be able to prove that our graph is having invariant lambda for strongly regular graphs and also having invariant mu for strongly regular graphs. Okay. Now, as I said, we found at the beginning, Coherent is not giving us name of the group. It is giving us just order of it. And this is order. And we were working at the beginning intentionally very naively. So we took classical book on permutation group theory by Dixon and Mortimer. There is appendix in this book. And in this book, there are all rank 3 groups with degree up, I believe, to 1000. And this is achievement which is obtained with the aid of classification of finite simple groups. So we opened this book and found what is our group, and it covers this extension of some simple group, classical simple group, unitary group, with subgroup of index 2 in its automorphism. So this was first way of our work when we were using knowledge of group theory and I will say of classification of finite simple groups. Not very pleasant, I call this activity use of nuclear weapons in mathematics. So now we would like to struggle in more fair way, without use of classification of finite simple groups. So we realize that there is a paper by, first of all, we take the home page of Andrew's browser, and we found from home page that there exists a graph with such parameters, and then we realized that this is our graph, and it turns out that there is very nice characterization of this graph, and what is characterization? Characterization is the following, that it belongs to family of so-called Sarah graph. Roughly speaking, axiomatic is the following, that we have in our graph clique of size 6, and we take any vertex which is not in this clique, and we found how number of vertices, of neighbors of this vertex inside of it, and this number should be permanent, and it is called nexus. And the nexus is equal to, in fact, it's much better. I was telling you minimal set of vectors can prove that all maximal x have the same size, the same nexus, and so on. So this created for us a challenge to prove as soon as possible to do this easy, that our graph, which is constructed, is the same object as Zara graph, and do not use computers for this proof. So some elements of this proof I will take. First of all, it turns out that in this classical Zara graph there is 576 maximal peaks. These maximal peaks are split into 3 orbits under the action of S7 into size 105, 210, and 252. We managed to give interpretation of each orbit in purely graph theoretical terms. Let's discuss one interpretation. 2 other interpretations are done in similar terms. So we consider disconnected graph delta 1, which consists of separate edge 0, 1, and of pentagon. Pentagon with vertices from 2 to 6. Now, we have to find click has to get size 6. So, click consists of this separate edge and of consecutive pairs of adjacent edges in pentagon. Clearly, we have 5 consecutive pairs. And remember that we are working in total graph. And in total graph, it turns out that it's really a click. Now we can count how many clicks are there. Easily counting shows us that in this structure there is 7 factorial divided by 20, 252 clicks. Similarly, we got interpretation of orbit of length 105 and orbit of length 210. So at least we now know that our graph has the prescribed amount of clicks, and if we will not, and if our participants will not be lazy, we have to check nexus. This is a little bit more routine job. Similar activity should be done, and after that we have honest proof without any use of computer that we are reaching Zara graph, because Blockhouse and Prover proved in brilliant paper that the properties of Zara graph define this graph uniquely up to that. Okay, and as I told, the graphs which we constructed, gamma and z are isomorphic. Now I think that I will skip most part of my slides, which are much more horrible. Now we have to decrease again to minus. Now I will see much more horrible things for probably 2 minutes. Okay. Right. Okay, so thank you. So now I will skip completely one part, which is really handwritten and it will be annoying to talk about it. And so this is one more model of Zara graph. This is a really interesting issue. Probably at least 10 circuits we see will be quite interested to see this model, because we are using a lot of results made by him in this group. We will speak about this. So we are talking now, and this is one of this model, not with standard graphic is here. Sorry that I don't have time to talk about this. And now, just a moment. Okay, now total graph coherent configuration for the complements of modules. A few minutes I would like to talk about this. So, a few times I was telling one of the foremost goals of the use of total graph coherent configuration is to start from interesting graph, to embed it to a larger graph, and instead of entering the initial graph, to work with larger graph. I would like to discuss with you why this is significant. Assume that our initial graph is Moore graph. Then, well-known results are that there is trivial case of pentagon, which is Moore graph of frequency 2. There is more interesting Peterson graph. There is much more interesting Hoffman-Simon graph of frequency 7. And there is open case 57 Moore graph of frequency 56. Nobody knows if such graph exists or doesn't. Regarding this graph, there was a lot of struggle. Struggle mainly was done by Russian school and school in Slovakia. And nowadays it is known that if such graph exists, Moore graph of frequency 57, then its automorphism group has ordered at most 375. Clearly, no way using computer tools to prove or to disprove existence of this graph, starting from suitable graph to a group of this order. However, we can try to make assumption that Moore graph is existing, to embed it to total graph coherent configuration. With total graph coherent configuration, we got a lot of experience. And with this experience, we are able to try to struggle. Who knows, probably we or our followers will be successful and they can able to find such structure provided it is existing. And this was exactly our way when we were working from Peterson graph with its total graph coherent configuration, and we found a new association scheme of order 40 on 40 points. This means with automorphism group of size 7, 6, 80, 80. And it was a very interesting challenge for us. We were not able to understand why this association scheme exists. And finally, the following result was obtained. Let me go ahead. So finally, we have association scheme on 40 points. We have automorphism group, and we, with the aid of CAP, are understanding that this automorphism group has the following algebraic structure: split extension of elementary abelian group of order 64 with S5. I asked my student, Sven Reifert, who recently enumerated all Schur rings over elementary abelian group of order 64, how many such groups are exist. And it turns out that there are 5 such groups. And it's quite difficult to describe one of them and to explain why this group is better than other groups. So we started quite sophisticated struggle to find a very clear and very friendly model for this concrete group. Finally, we managed to do the following. We realized that our group is a subgroup of automorphism group of so-called hexagroup. Hexagroup is a living in the site of Mikhail group of degree 24. This is automorphic group of famous V design of 24. So finally, we realized that we have to go to very artificial structure inside of V design, which has one orbit of length 4 and one orbit of length 20. And in terms of this artificial structure, using classical knowledge of V design, we are able to explain everything about our associations. This is very roughly a story which I omit due to the struggles, but at least I am happy that I was able to finish this lecture. If you will allow me to use half of a minute, I will be very happy to do this. My favorite Russian poet, Boris Pasternak, has the following sentence. I will start from Russian. Но поражение от победы никто не должен отвечать. Translation to English looks as follows. You have to act in such manner that nobody will be willing to distinguish between victory and defeat. In this situation, I was forced to defeat. And I was doing all my best to try at least to make small movements towards victory. I do not know if something I managed to do, but thank you very much for your patience, for your tolerance,